Okay, let me describe the architecture of my MapReduce Paxos project for my distributed systems class. So you may have the code already. Here's the code. The whole project is in this directory, and in the doc file there's a MapReduce replicate. This is the problem statement. By the way, there's a README also that has instructions on how to run it if you don't want to watch this whole video, and there's also a link to a video of me running it if you don't even want to run it yourself. So let me just tell you about what the project is, first of all. So there are 3 different computers, each of which is running a mapper and a reducer. In principle, these could all be on separate nodes, but just for the sake of this project, each computer has a couple of mapping processes and a reducing process. And the idea is there's going to be some file that the mapper is going to take the 2 chunks of that file and essentially count the words in that text file. Make sort of a tally of the words in the first half, a tally of the words in the second half, and the reducer, send them to the reducer. The reducer is going to merge those 2 word count tallies together, and that is going to be done on each of 3 machines. Asynchronously, this is going to be controlled by essentially a command line interface to each of the 3 machines, and the result is that these 3 files have their words all tallied up in these 3 essentially dictionaries, and then the Paxos replicator module. We're going to use Paxos, the distributed consensus algorithm, to insert these 3 word count tallies into 3 positions in a replicated log. So just to give you a little more background on what's going on there, the map command, here's some document. So this is running on one node. On one node, there's one document, and when you map that document, it chops it up into 2 parts, sends those 2 parts to 2 different processes, 2 different mappers on 2 different processes, and those mappers essentially just append a little 1 to every word in that document. So this is not a very impressive thing. This is just, I think, because the MapReduce paper, the OSDI 2004 paper by Jeff Dean, uses this as an example. You don't even tally anything. You just sort of put the number 1 there, and it's up to the reducer here to take all of these little instance counts here and then take these 2 different files of these instance counts and merge them together to make a real tally of the words in that file. And once you have this sort of dictionary of word and word count pairs, you can then hand it over the fence to the replicator, which is running on the same node on a different process. And that replicator has an array of 3 elements, and each element is a dictionary of the file name, and the key for that, the value for that key is the dictionary of word counts for that file. So this would be, the Animal Farm, and this, the book, and the word Animal Farm.txt, and this is the tally of words, the words that appear in Animal Farm.txt. This is some other text file and its word counts and so on. And the point of this is that we have to use Multi-Paxos, that algorithm, for to have this computer and this other computer on this other node and this other computer on this other node are all going to have to agree on what's in. They're going to have to run Paxos essentially for every element in this 3-element log, and so those logs should always be the same across those 3 Paxos nodes. So that's the idea. Okay, so let's see. Is there anything else to show you here? I don't think so. Is there anything else to show you here? Okay, so just the workflow in this sort of swim lane diagram is on a single node. The client, this is my distributed systems TA, Victor. He was very nice to let me put his picture up here. The client is going to be interfacing with some command line interface that's going to be running as a process on some port on this node. And that command line interface, you'll say things like, I want to map this file, and that command line interface will send the first chunk of that file to the first mapper, the second half of that file to the second mapper, and they're going to essentially append these 1s to the words and then write them to these intermediate files. Then from the command line interface, the user will say reduce of these 2 intermediate files, and the reducer will read these 2 intermediate files that you listed here and produce another file which is like the dictionary of word counts. So it'll be like the keys are all the words in the text file, and the values associated are the associated counts of those keys. And it'll tell the CLI it's done. And then finally, the user will say replicate file reduce. So this is some text file that is a dictionary, and the replicator module, this is the crazy part, the replicator module runs Multi-Paxos and essentially attempts to insert that key value pair, the file name and then the counts, into the 0th element of the 3-element array using Paxos. And if that works, then that's great. Then you got that file name and the word counts in the 0th element. And if not, you got to try it again for the first element and then try it again for the second element. And hopefully if there's an available element, then what will happen is all of the nodes, which are all running Paxos, will agree that they have put in this particular file name into some element in the array. So that's the workflow from the client's perspective. Okay, so let's show you the code. The code starts with this copy to Eucalyptus. Eucalyptus is the cloud computing infrastructure that we're using for this project. Let's see if I have a picture of what it looks like. When you have it running, the web interface for it looks like this. So we have a publicly facing IP address with one machine, and then through that we copy our files over onto 3 private IP addresses and run it all in there. And that's mainly because Eucalyptus doesn't have enough publicly facing IP addresses for everybody to have 3 or 4 for every group in this computer science class project. Okay, so you can, once you're logged in, you have 3 different terminal windows, and you can SSH in and screw around on 3 different virtualized machines in this cloud. Okay. And so the first thing to do is to run this copy to Eucalyptus script, which has the IP addresses hard-coded in here. It has the SSH keys that the cloud website generated for us, and we essentially nuke and pave. We're going to wipe out everything in the public one, and then copy everything over. And then for every private IP address, we're going to SSH into the public one, and then SSH into the private one through the public one, wipe it out, and then SSH everything over onto it. So this is really brute force, but it gets the job done. And so let's show that now. So, and I don't have to enter any passwords because we're using the we're using SSH keys. Great. So once that's done, we will then run the program. And I'll show you the program. So what we're going to do is essentially there's the 3 different private IP addresses, and then the command line interface, the 2 mappers, the reducer, and the Paxos replication module are all different processes running on each node. In principle, if you had 15, there are 15 things here. If you had 15 different IP addresses and port numbers, you could use those. These could all be running on different machines. There is you would, if they were running on different machines, you would have to do a little bit of work to coordinate these, because in this case, for example, the command line interface provides a file name to the mapper. The mapper expects that file name to be on its disk. So there would be some work if you wanted to distribute these to 15 machines, but having them all be on a node was sort of how the problem statement was arranged. And so then we do these complicated. So for each of the 3 nodes, we first run a command that just makes sure that we kills all of the open sockets. So this is sort of a last-minute brute force thing that I had to do to make sure that if any of my programs crashed, that we could wipe out the sockets to sort of clean up the environment. Each of these xterm commands will open a nice, cute little window. So we're actually going to have 15 windows up here. And then what we're going to do is run bash in that xterm window with the command that we're going to SSH into the public IP address. Then from that public IP address, SSH into the private IP address. And then we'll run the command line interface, the mappers, the reducers, and the Paxos replication module. The command line interface needs to know its own IP address and the IP addresses and ports of the other of its other nodes, and the other guys essentially, the Paxos guy has to know, oopsie daisy, the Paxos replicator module needs to know the IP addresses of his friends, of the other nodes that he's going to do Paxos with. Okay, so that is this. I should point out here that although it's important to not repeat yourself, to have dry code, I think it's actually more readable here to have it be repeated, and you don't have to worry about about having copy-paste errors, because Sublime Text is just so good at having multiple selection windows that you can, if this needed to be 500 or something, or 300, I wouldn't have to worry that I was not typing it incorrectly here. So that's my plug for, it's important to have dry code, but there are certain situations where having repetition actually helps your eye to see the structure of a program. Okay, so that's my little blurb here. The kill open sockets thing is just a brute force way to wipe out a bunch of sockets. We use LSOF to find out who's tying up my sockets. It's probably Python 3, and we'll wipe it out. There's a debug module that the code uses. Actually, I should jump over at this case and actually run Eucalyptus. What that's going to do is fire up a bunch of xterm windows. The first row is for the first node, the second row is for the second node, third row is for the third node, and the columns are the CLI, the two mappers, the reducer, and the Paxos replication module. So I can ask for help. I'll say map data. Actually, let me say, so I have this data file here. It's a pretty short data file. I just did it so you can easily get a tally of the words in the data file. If you say map data /f, it sends those out to the two mappers here, and you can see that it has produced the two intermediate files. You can then ask to see the data, the intermediate files, and you can see that they're just appending ones to all of the words in this data file. Then you can say reduce data fi1, data fi2, and that will kick the reducer into gear, producing data /f reduced. So let's see what that looks like. And this is a tally of all of the letters in the original data file. At this point, you can then kick Paxos into gear. You can say replicate data /f reduced, and that causes Paxos to kick in. It has communicated with the other nodes and made this in the first log entry. So if I say print on the other two nodes, you can see that that log entry has been replicated across the other Paxos nodes. Here I'll stop this Paxos node, and now I've already run the mapper and the reducer on this node as well. So if I say replicate data /h reduced, that will make the Paxos algorithm run here. You can see that log entry 1 has the reduced file name and the counts in that file. So just so you can see, data /h is a bunch of letters from sort of the last part of the alphabet, and it's gone in log entry 1. You can see that it hasn't showed up here because the Paxos algorithm, the Paxos has stopped on the second node, but it has been replicated here. And by the way, you can do all of the sort of checking things where you add up the total number of words. You can merge together the two, different the two different log entries, and that works on that works on all of them like this. Okay, so now here's the big idea. I guess let me replicate replicate data. I'll replicate h reduced again, so you can see here that it got replicated again. It is also here, and so now all three log entries are filled up. So now if I resume the Paxos, it essentially proposes a dummy value, and in order to sort of get up to speed on what it's missed since it went down. And you can see that it did retrieve all of the missing log entries, and you can ask it to print it, ask it to add up the total number of words, merge all of the entries and so on. I think you can even merge all of them together and get a total count for all three. So that's the project. Thanks very much. Oh, I should mention that it is possible, so the real test is if you start two nodes trying to replicate at essentially the same time, will anything break? And so let me show you that right now. So let me kill everything. We'll start it all over again. I still have the replicated files on disk here, so I can say things like, I can say replicate data /f reduced. I could say replicate data /g reduced, and replicate data /h reduced. So if I can somehow do all three of these things at the same time, we should see that all of the logs are still consistent, even though Paxos will be fighting to try to get them all all in the same log entry at the same time. So I'm going to just try to get all these things running at the same time. Okay, so I had them all attempt to replicate. Let's see how it actually played out. So they should all have the same log at this point. And let's see. So it looks like it looks like we got the first part of the alphabet in log entry 1, the second part of the alphabet in log entry 2, and the third, the H file in log entry 3. And it looks like they're all the same. The log is the same for all three Paxos nodes. There. I hope that's sufficient. Okay, so now let me talk about the code, the structure of the code. So we have the command line interface, the mappers, the reducer, and the Paxos replicator. And all the code is right here in these tabs here. So there's a debugging module that essentially gives you one way to turn on and off debugging, like debugging print messages, that essentially just prints out the time and the message. Fine. I'll get back to the networking one because I want to show you the sort of from the top down. So the mapper uses the mapper and the reducer and the Paxos replicator all use a function called a worker that is in this networking module that I wrote. So and each of them, all this does is essentially it binds to a port and then listens for messages to come in on that port, and then we are in a very brute force way, we're just using one TCP connection per message. And so a client will connect to that port, send a message, which is I implement as like a pickled Python dictionary, and then just close the connection. So the worker, in a very basic way, receives a message and then sends those bytes to the parser. So a worker is given the address that it's supposed to bind on, and then the function that it will feed all of the bytes to. So let me just show you this as an example. Okay, so here's the worker. The worker, essentially, you give it an address and a function, and it is going to bind an IP address, listen to accept a connection, read all of the bytes, all of that connection while true, essentially until the connection is broken, and then just feed all of the bytes to that function. And that function may return a reply message, in which case it will send that reply message back up the stream. So this is for if you have to implement simple acknowledgments or something. Okay, so that's what a worker is, and a mapper just essentially uses a worker in the following way. All the mapper does is it defines this parser function that is going to take those bytes, unpickle them. If it's a kill command, it'll exit, and otherwise it expects the unpickled dictionary to have a file name, an offset, and a size. Okay, because those are the three things that the mapper requires. Besides its identifier, it's either going to be 1 or 2. And all this mapper is going to do is going to open the file name and essentially put just the word, comma, 1. Just like you saw in the picture back there, for every word in the file, and then write that to file name underscore I underscore and then your mapper ID 1 or 2, and write that to file as a JSON formatted file. So that's all a mapper does, and it will do that every time it gets a TCP connection with a bunch of bytes. It'll unpickle it and attempt to map that file name. Okay, so that's what a mapper does. Let's talk about a reducer. A reducer is the same kind of thing. It just starts a worker that parses the bytes that are given to it. What does the reducer's parser do? Well, if it's supposed to kill it, then it dies, and otherwise it tries to interpret that thing as a dictionary and is given a list of file names, and then it reduces that list of file names. What does it mean to reduce a list of file names? Well, for every file, open it up, grab the word, make a counter, and essentially tally it up. So we're using the collections.counter class for that. And then essentially write that out as a JSON file to disk. So this will be a tallied up list of word counts. Okay, so that's all a reducer does. Now let's talk about the command line interface. The command line interface needs to know not only its own IP address, but the IP addresses of the mappers, reducers, and the Paxos replicator. And all that thing does is, while true, it's going to listen to the standard input for a command from the client, from a human, and then based on whether the command is help or map or reduce, it's going to essentially take the rest of the tokens in that line and send them to the mapper or the reducer or whatever. And it's going to use this network.send method to do that. You can see that it takes essentially an IP address and a port and a dictionary. So let me show you what network.send does, because that's the only other function in this module. Essentially, it's going to take an address and an object and a reply function which defaults to none, and it's going to attempt to create a connection. And every second it's going to attempt to create a connection with that address. So hopefully there will eventually be a listening process on that is bound to that socket. And once it makes that connection, it'll just pickle up the object and then send that through the channel. And then if you have supplied a reply function to send, then it'll wait for a reply. Hopefully the replies aren't more than a kilobyte, and call a reply function on it. So we use that reply function up here the bytes that we get back from the mapper and back from the reducer that are given to the command line interface will essentially inform the command line interface about the status of whether the mapper was successful, whether the reducer was successful, or whether as we'll see, the Paxos replicator can't execute the entire Paxos round while it's also waiting on the CLI, so it'll just enqueue that. So anyway, so this is essentially to tell the user what happened when we told the mapper to start or the reducer to start. Okay, so that's really all the command line interface is. I just copied all of the spec for the commands that the user is supposed to be able to execute and put them in this file here. And then I put in some other extra commands for helping with debugging. So that's the CLI. Okay, now let's talk about the Paxos replicator. So as we were talking about before, there's a CLI, a mapper, a reducer, and a Paxos replicator. So the Paxos replicator is the thing that coordinates the Paxos algorithm across the 3 different arrays, each of which will hold a dictionary of a file and a word count. Okay, so all the Paxos replicator does is it gets its own address and then the addresses of the other Paxos replicator modules. It makes a Paxos replicator object, which we'll talk about in a second, and then it needs to asynchronously be able to dump messages from the PRMs and from the CLI into some queue, into some global queue that it has access to, and so its parser essentially just puts messages, it loads up, it unpickles bytes and puts them into the queue. So hopefully these will be dictionaries when unpickled and they're put into the queue. And I know you're not supposed to, unpickle things from untrusted sources, but so far, we're only going to be, this is like a class project, so that's like to do. Okay, and then in a separate thread, we'll spin off this network worker, and he'll listen on this address and dump bytes into this parser thing, which will put them into the queue. The PRM is going to fill up an array full of log values, and what a log value is essentially just a file name and a word count. I didn't implement them as a dictionary because I needed them to be hashable, so I had to implement an equals method and a hash method that essentially just crunches up, that hashes the log value. Okay, so now getting into the meat and potatoes of it. The Paxos replicator is really just more of an interface to the rest of the command line interface and whatever. The thing that actually implements the Paxos algorithm is this thing called a Paxos node, and that separation was very important for debugging because it allows us to test whether or not the Paxos algorithm works, which is really hard and complicated, without having to hook it up to the rest of the network or the CLI or anything. So I'll get into that in a second, what a Paxos node is, but essentially a Paxos replicator has like 3 Paxos nodes, however many there are however many entries in your array you need to reach consensus on. That's how many Paxos nodes you need, and the other PRMs will have a corresponding number of Paxos nodes. And all this Paxos replicator does is it just runs, waits for messages to come out of the queue, and then receives them, essentially. So if it's supposed to replicate, then it calls replicate. If it's supposed to stop, it calls stop. And and all that really does, and I should point out that if the dictionary has a Paxos key in it, that means that's my convention for this is a message from another Paxos replicator module that contains a message that is involved in the Paxos algorithm itself. And so in that situation, if it's not a command like from a CLI to tell you to stop or resume or whatever, if it's a Paxos command essentially, then if this replicator is running, then it should send that Paxos message to the appropriate element of its array. It should call receive on whatever Paxos node was indicated by the message, by that dictionary, and it should give it the message. So we have sort of a message within a message. And that's how I implemented the fact that the PRM, the Paxos replicator module, needs to be able to coordinate with the rest of the network, like the CLI, like the command line interface, but it also needs to coordinate the exchange of messages for the Paxos algorithm for each of its little Paxos nodes that it holds. Okay. So I will just very briefly go over what happens in the replicate method, which is kind of the most complicated method. The idea is this is the method that the CLI issues to the PRM that is supposed to kick off Paxos. Which version of which Paxos node is it supposed to kick it off in? Well, it starts at 0. It starts at 0. So for enumerating all the Paxos nodes, it's going to start at 0 and try to get the 0th Paxos node, its 0th Paxos node, to initiate Paxos and get consensus on what should be in the 0th array entry. And if that fails, it's going to try to on the first Paxos node and get the first array entry to get consensus on that value. And then it'll try the second one, and however many elements there are in the array. In this case, there's 3. So I won't go into the details of this, but let's just say that that's what it does. It goes through each array entry, and if there is consensus on it, if it's none, it is going to try to get consensus on the corresponding array element, and it's going to march through the dictionary trying to get consensus until once it finds an empty entry. Okay, so that's what this one does, and I'll let you look at the code longer if you want to do that. All the rest of the methods are totally boring. You can stop the PRM, you can resume the PRM. Once you resume the PRM, it needs to get up to date on what it missed, on what log entries maybe the network got consensus on while it was stopped, while it was sleeping. And so it replicates, it attempts to just propose, it initiates Paxos with a dummy value that will serve to get the rest of the network to fill it in on what it missed. Okay, and then there's some data query calls, like if you want to ask total, what that essentially does is it adds up the number of words in the counts in all of the log entries. So these are not especially interesting, but they serve as a way to test to make sure that the replication worked. Okay, so what remains now, the last thing to do is to talk about what it means for a Paxos node to initiate Paxos. How does it run the Paxos algorithm? And that happens here. So so there are two things, as you know, especially if you've seen the Paxos in Pictures video that I did. You know that the Paxos algorithm has this thing that's essentially a number in the prepare request, and here you can just use natural numbers as Leslie Lamport does in his Paxos Made Simple, but because you need the natural numbers to be unique across all the PRMs, you also have the process identifier in addition to just a counter. And so this thing is actually not just a number but a pair, and sort of for convenience, I didn't want to just use pairs like tuples. I wanted to have an actual object for it so that you could recognize it and stuff and have it print out nicely. And so anyway, so it's totally ordered, which is very important for the algorithm, and it's also hashable. And you can add like things to it. I don't think this ended up being useful. The other data type in the Paxos algorithm that is talked about in Paxos Made Simple, besides the number of the proposal of the prepare request, is what a proposal. And what a proposal is essentially a number, like a num number, and a value. And this thing could be anything. This thing could be any data type. These proposals are totally orderable because you're using the num to totally order them. So by defining less than and equals, you can get a total ordering on them. And they should also be hashable for the purposes of having them be in dictionaries and stuff. Okay, so those are the two data types that are used in Paxos, and now we're ready to talk about, and this is the end of the file by the way, we're ready to talk about what is a Paxos node. So these are all folded up functions here. I folded them up. You can see that this is, these are much longer methods, but I'm trying to point out that there is the proposer methods are prepended by a P, the acceptor methods are prepended by an A, and the learner methods prepended by an L. So all these methods essentially, the proposer starts a proposal by sending a prepare request. The acceptor then receives that prepare request and generates a prepare response. The proposer receives that prepare response and generates an accept request. The acceptor receives an accept request and sends to all of its learners a decision message. The learner receives a decision message. So these pairs of methods are all directly come from the Paxos algorithm as outlined in the Paxos Made Simple paper. And so, just to be totally clear, they in the paper they actually say, phase 1A is a proposer selects a proposal number n and sends the blah 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 blah. And I just pasted that in here when I was first getting started and just directly implemented it. And I'll talk about the details a little bit. There's one subtlety that I'm really proud of that I want to share with you. But so this is phase 1A that sends a prepare request message, and so down here is phase 1B, when the acceptor receives that prepare request message. What does it do? It sends a prepare response message. That goes back up to the proposer. He receives the prepare response message. Let's go up here. Prepare response message. And then that's, if you remember the paper, that's phase 2A is when the proposer receives the prepare response and then it sends out an accept request. So there's some complicated things that happen when the proposer receives a majority of acceptors' prepare responses. It essentially gets to fire out a new value, a new proposal, and then it sends it out as an accept request to the acceptor. So that was phase 2A. This is phase 2B, what happens when an acceptor receives an accept request. So I tried to make these things just absolutely foolproof by having them have the same names as in the Paxos Made Simple paper, which is probably the most viewed paper for how to get started with Paxos. And then very lastly, phase 3 is essentially when a learner receives a majority of decisions from a majority of acceptors. So that's down here. So the learner, the acceptor then sends a decision message to each learner, and that happens down here. And so this is sort of the most critical part here. Once the learner receives decision messages from a majority of acceptors, then it can set its value. So the self.v is the value that the Paxos that is the output for this node's Paxos algorithm, and that's the most important value in this entire thing. That determines whether or not the consensus was reached or not. This is the last thing that is written essentially in the Paxos algorithm. Okay, now there's one last thing I want to point out here because I think it's subtle, but I think it's really an interesting. I think it's an interesting way to architect this, and that is the Paxos how we do the communication. Notice here that there's a send method there's the Paxos nodes are allowed the way that we work it is the Paxos nodes are allowed to send messages to themselves, and that makes it easier so we don't have to repeat code when we're sending when we're trying to get Paxos nodes on board with their own requests. We have them act as just other nodes. That happens up here essentially in the init. We have the proposer's list of acceptors be himself and whatever else was given. We have the acceptor's list of learners be himself plus whatever other learners there are in the network. And we have every node be a proposer, acceptor, and learner. Okay. So the whole point here is that there's this if you're sending to yourself, you can just directly call your own receive method. But if you're sending to another node, how should that work? There's this send method, and that send method comes from here, which is set to send function. Now this send function is the most complicated part, I think. The send function is a method that takes as an argument that is what the Paxos node is going to hand over all of its dictionaries to when it is going to send a message from itself to some other Paxos replicator module. So all this send method needs is it takes one input, which is a dictionary that has a from and a to key, and does the appropriate thing with the message. So the reason this is subtle is because it's important to have it this way because it lets you debug it without having any network connections set up. And here's an example. Here's a one-page example of how to run Paxos without needing any network connections at all. So we're going to make 3 Paxos nodes. This one has name A, name B, and name C, and here are his friends, AB, AC, and AB. Now here's the part where we send. This is the send function that we're going to provide. It's a lambda function, so you give it a dictionary, and it's going to call send, which is some function we define here, giving it the dictionary and then the 3 nodes. Send takes 3 nodes, and if you're supposed to send it to A, then P1.receive, and you hand it the dictionary. If you're going to send it to B, then P2 receives the dictionary. If you're going to send it to C, then P3 receives the dictionary. So this is this is a way of having the Paxos nodes have a method that does not require any network activity, but still allows the network nodes essentially to directly call each other's receive functions and hand them the thing. So for example, P1 is going to send, if P1 wants to send a message to B, then there's going to be the to key in the dictionary is going to be B. So this line is going to get called. And what that's going to do is it's going to call B's receive message. Receive method, giving it the dictionary. If P2 needs to send back to P1, well, there is a from key in the dictionary here, and P2 can then call send, which is the exact same lambda function, giving it the where the to key will be the from key from the original dictionary, and this send method will just call P1's receive message. So this mechanism allows nodes to directly call each other's methods without needing any knowledge, without needing direct access to those nodes. So you don't have to worry about contamination, like one node screwing up another's private variables. They do all, and you also don't need a network connection. You don't need to bind anything here. Okay, so let me just show you an example here. So this makes the 3 Paxos nodes. Beforehand, let's just print them out. We'll initiate Paxos with this value. We're going to try to get this value to be distributed around the network. And after P1 initiates Paxos, let's see what they all got. And then once they reach consensus, the whole idea is they're not allowed to change. And so if P2 initiates Paxos with some other value, we will see that they will not accept that subsequent value. So let's run that and see that we actually get that. So initially, all of their values, their maximally numbered accepted proposals are all none. After P1 runs, the value that they've accepted in their maximum accepted proposal is a proposal with some number, who cares what it is, and the value is P1's awesome value as specified here. And they all agree on this. P1's awesome value, P1's awesome value. Okay, and then after P2 tries to initiate Paxos, you can see that the value has not changed. They're still all on P1's awesome value. They did not receive this second value here. So that's the whole point of Paxos. Okay, so that is how to test this Paxos node in a single page. You don't need any network, anything. You don't need to give the nodes access to each other's self-direct objects. You can just use this sort of funny redirection trick, which I was pretty proud of. I think that was subtle but very effective. And the way that it works when you actually have a network, you're not going to use this funny trick that in the one pager is you'll give it a lambda function where you take the dictionary. This I equals I thing is just a consequence of how Python binds objects when it whether it does it at the definition time of the lambda or whatever. And what this lambda function does is it calls this network.send. It sends it to this address and it gives it this dictionary. So whatever the Paxos node wanted to send, that dictionary gets wrapped up in another dictionary that is sort of a, that envelope goes in another envelope where that corresponds to, that is tagged essentially with the correct index of the Paxos node. And it's tagged as a Paxos message, so that when the Paxos replicator receives on another machine receives that message, it knows to hand it directly over to the corresponding Paxos node and call its receive message. So that concludes the structure of the code. Just to conclude, there's the command line interface, the mapper, and reducer. These are all pretty simple. This is essentially just a giant while loop that listens to commands. The mapper is essentially a one-page, thing that just does a little data processing, and it uses this worker thing to sort of wait on a port. The reducer is exactly the same thing, only with a slightly different function in there. The big part of this project was getting Paxos to work, and we tried to get Paxos to work in a way that was as close as possible to the paper Paxos Made Simple, and we architected it in a way so that you could call it directly on just a very simple, almost directly on the objects themselves, but with a very simple redirection mechanism that allows you to easily, instead of giving it a lambda function with a simple send function, you can give it a lambda expression that has it send out actually a network. Okay, so thanks very much for listening. I hope you enjoyed this code overview.